And I need to share this and go here and go here and use this. Okay.
Oh, I don't see the mouse. Oh, okay, here you go. Okay, well, my honor, my privilege to be here to present some of the research findings from our lab. It's a teamwork. I didn't list everybody's name here, but definitely there's a lot. Volunteers, student workers, including our former research associate, Dr. Hook, Tristan Hook. I believe that he's joining online today. He's now assistant professor at the University of Arizona. So a lot of people contributed to the research work on the microgreens here. And we've done a lot of studies. I probably won't have time to share the results, all of them. I just picked one or two. We'll see how the time goes. I have to confess, I finished my presentation last night late and I didn't practice. So we'll see how the timing, I have a tendency to probably put too much content for the short presentation time period. First, for those not familiar with what's microgreen, there's a lot of definitions out there. I like this one. It says it's a young and tender edible greens produced by sprouting the seeds of a variety of vegetable species, including the herbaceous plants, herbs, or some of the wild edible species. Most of the microgreens normally harvested just after the cotyledon fully developed. Some can be harvested with the first or second true leaves. The microgreens are mostly used as enhancement to the dishes due to its very intense flavor and also its high value nutrient. It has a very strong flavor, aroma. Also, it's sometimes used as a visual enhancement as dishes. Want to talk a little bit about why we are interested in the research on microgreens. Before I started working here 2 years ago, I had no idea what's microgreens. Until I started doing research on that, I get the opportunity to taste the microgreens. It's just amazing, delicious. I love the microgreen taste. Plus, it's packed with 4 to 6 times the nutrient value compared to the same crop, the same mature plants, leaves. Although the cost probably will be 3-4 times or higher to produce it, or to the sell price, if you want to buy microgreen from the grocery store or market, will be a lot more expensive. But with the technology development so fast, and just think about LED lights 5-10 years ago, where anybody use it, but now it's just everywhere. The cost is significantly reduced now, so I think the microgreen will grow popular in the future as well. Just imagine, I often envision, on the airplane, when you are taking airplane during the flight attendant, instead of serving you pretzel, normally that's the snack that they serve on the airplane, right? If they serve you microgreen, how that would feel. I'm just very excited about that idea. It's such a healthy snack, although right now the cost might be higher, but I'm sure in the future there will be one day they will serve that instead of the pretzel. The first study I'm going to share is about the far-red and the UVA, how that affect the microgreen growth in the controlled environment in the indoor growth chambers. Just a review, quick review. I think Dr. New already mentioned a lot earlier in the sunlight was the composition. For the experiment, we're going to use the UVA, which is between 315 and 400 nanometers. And then far-red, it's just within the very far end of the visible light, between 700 and 770 nanometers, the wavelengths. There's also other UV lights. There's a lot of research has been done on the UVB, but not a whole lot has been done on the UVA. Most of the UVC used for disinfection in different industry. Both UVA and the UVB can be harmful to people, but not as harmful as UVC compared to UVC. UVA and the UVB is relatively safe. The study, we have the hypothesis is if we add a UVA for the production cycle, we can probably increase the quality, mostly like a phytonutrient. Phytonutrient is certain chemicals produced only by plants, including like pigmentation, antioxidant, all the good stuff that's good for your health, to prevent aging, to help boost your immunity. It has a lot of benefit to people. There's a research have been done in the past. If we're adding the UVA to the growth cycle, it could increase the phytonutrient value. The level of the phytonutrient level can be increased. Although there possibly can be some other negative effect, like a suppress the growth, get a shorter stems, plant height. There's some other possible effect that could reduce the yield. Then we thought, okay, if adding the UVA during the whole production cycle might possibly have some negative effect. What if we just add the UVA at the end of the production cycle, closer to the harvest, for a short period? Would that have any effect? Would that have more benefit and without any negative effect? So that's why we interested to test that. For the far-red, it's well known the far-red light will increase the stem elongation, where it's called the shade avoidance effect. It will cause stretching. In the microgreens, it would cause longer hypocotyl, which is from the seeds to the cotyledon, that length of that stem called the hypocotyl. So the far-red could increase hypocotyl length, which is count as a major part of the microgreens. When you harvest, is mostly the stem and the cotyledon. Then that would give you a higher yield, a higher fresh weight. The last hypothesis, if we add the far-red during the total production cycle and the UV at the end of the production cycle, then we hope we can both increase the yield and the quality of the microgreens. Here's just a brief summary of the experiment, how it's set up. In this particular study, we used 8 microgreens. They were grown in small inserts, 10 by 20 inches tray. And each insert is only 10 by 10 centimeter. One tray, it's a pretty standard 10 by 20 inch tray is pretty standard. So there's 8 inserts in each tray. And we use the only one substrate. It's a grow down crest plate, which is rock wool. The material is rock wool sheets. And then we have a 6 light treatment. The 6 light treatment, they're all the same. The total light intensity is the same, but a different spectrum. We have 4 replications for each treatment. For the growing environment, we try to keep it the optimal for the microgreens. The average temperature for the whole growing cycle is about 21.6 Celsius, around 71 Fahrenheit. Humidity varied between 45 to 77, and the average is about 61%. This is just give you the detail what 8 microgreens were used. There's most of them are brassica. There's a kale cabbage, they're actually the same species, and we use this is the actual seeding rate we used. Have to clarify here, the seeding rate we actually use is slightly lower than what the seed company recommended. Here's just a reference. Normally, how many days those microgreen will be harvested from seeding to harvest. Most of them has a similar growing cycle. The only one that's grows slow here is basil and cilantro, which is a longer growing cycle from sowing to harvest. When we had a study, we actually had to sow different species in stage, different dates, so that way we can start the treatment at the same time. Here's the detail of the light treatment. All the 6 treatment, the lighting period is 12 days. The whole growing cycle for the study is 16 days. So the first couple days during the germination period, we were not turning the lights on until everything germinated. We start turning the lights on. And then for the UVA end of the production cycle treatment, it's only 5 days for the last 5 days of the growth cycle. So during that 16 days, it's only last 5 days we have the UVA added. This is the breakdown. How many PFD, what's the light intensity for each spectrum we used for this study for each treatment. Have to tell this number is the actual light intensity PFD, the photon flux density, which measures the light intensity, not the percentage of the light composition. But then you can calculate, let's say here in the white light treatment, we have a 49 PFD. The total PFD is 150, so that's about 1/3 of the 30% of the this treatment is a green light. You can look that way. Here is just showing you how each treatment, where's the peak. It's the same thing as the table just showed the previous slide, but this one is more visual, give you showing where's the peak for that treatment of the particular light. like for UVA, we have the peak at the 385 nanometer, which is within the range of UVA. And then for the FORAT and the UVA combination treatment, we have the peak of the UVA at the 385 and the peak of the FORAT at the 739 nanometer. Here's the results. If I have those letters, they are different, that means statistically there's a difference. But if the letter is the same, then there's no difference. This letter showing the yield or the fresh weight we measured. Visually, you can see the white light treatment, which we consider like a control. That's the most commonly used in any controlled environment production. This is the plants the same as grow more compact, smaller, and all other treatment with a different spectrum. They are slightly bigger, and particularly the ones, the 3 treatment that has a FORAT, you can see they have a longer hypocotyls and just the taller plants. For the basal, there's no significant difference between the treatment. I think that's probably because basal normally require longer crop cycle, which our study is only 16 days, which is at the very lower end of basal crop cycle. For cabbage, there's no significant difference in the yield either. Even though the growth, the morphology is slightly different, you can see the FORAT still stretched more. The other ones with UVA is more compact, but the total fresh weight, there's no big difference. For cilantro, most of the treatment except the UVA for the whole growing cycle is the same as the control, but all other treatment has a higher yield compared to the control. For kale, the one with the FORAT treatment during the whole growth cycle actually has the lowest yield, but still this one is similar to the control. The best one, the highest yield is the FORAT with UVA at the end of the production cycle. For kohlrabi, there's no difference of the total yield between the treatment. So for Mizuna, again, the control is the lowest yield. All the other treatment is slightly better. Although the FORAT and the UVA during the whole production cycle or the end of the production cycle is still the same as the control, but not less. For radish, the UVA treatment at the end of the production cycle actually has the highest yield. Here's a look at the height, how each treatment affect the plant growth. For arugula, all the treatment with FORAT, you can see they're significantly taller than the ones that didn't have a FORAT in it. Although the one with UV, regardless of the whole production cycle or the end of the production cycle, they still has the same height as the control. For basil, similar results there. Or basil is the one actually you couldn't see a whole lot of difference. Again, like I mentioned, the basil require a little bit longer growth cycle. Our study is a little bit short. You can see the one with far red still taller, but not really a whole lot of taller. Cabbage, there's some differences. Again, the one with the far red is the tallest. Same for kale. Kale and the cabbage is very similar results. Here's the radish. For radish, kohlrabi, misuna, and the cilantro, all those four similar. The one with the far red has taller plants. The one with UV and the control has shorter plants. Got to go back one. Going too fast. Here's the look at the phytonutrient for the total phenolic content. We only see the cabbage and the misuna with the UV treatment during the whole growth cycle. It's just significantly higher than the other treatment. For the antioxidant, it only has a difference in arugula with the UV treatment at the end of a production cycle, and in basil, it's the one with UV during the whole production cycle has significantly improved the antioxidant content in the microgreens. So the conclusion, just the summary, what we see in those pictures, the UVA did not really decrease any yield in any of the microgreens that we studied, either applied during the end of a production cycle or the full production cycle. And UVA significantly decreased the height in cabbage, cilantro, kale, and the kohlrabi and the misuna when applied for the full production duration. We also see the far red increase the height in basil, cabbage, kohlrabi when applied for the full production duration. Also, we see UVA increase the total phenolic content in cabbage and the cilantro, and increase the antioxidant in arugula and the basil. So the take-home message from this study, with your UVA, it can be a potential tool to enhance the microgreens of phytonutrient value, either applied during the whole production cycle or the end of the production cycle without any negative effect on the yield. Also, we see the potential of using both far red and UVA as a tool to control the microgreen height without negative effect on the yield. But again, different species, different microgreens, their responses to the light treatment, different spectrum, differently. It's species specific. Okay, my time is up. I got to stop here.
Thank you very much. Thank you very much.
Thank you very much. Ling is available to answer